Electronic markets operate on a massive, high-velocity avalanche of unstructured data. Millions of interactions are recorded every second, in the form of high-frequency trading logs, image matrices, and endless text streams. Early computational systems attempted to manage information through explicit programming and rigid, rule-based logic structured market data. Historical knowledge-based approaches failed because humans struggle to explicate all of their tacit knowledge into a formal programming language. We intuitively recognize a pattern, but we lack the precise syntax to define it for a machine. Surviving in modern electronic markets required abandoning human-written rules entirely. The systems needed to operate here must learn autonomously from the data itself. Artificial intelligence is the broad systemic capacity for computers to mimic or exceed human decision-making in complex tasks. Artificial intelligence forms the outermost boundary. Nested inside is machine learning, automating analytical model building through iterative experience. Deep learning occupies the innermost subset, powered by artificial neural networks. A dashed boundary separates shallow machine learning from deep learning, distinguished entirely by processing architectures. Deep learning involves a technical transition away from shallow machine learning. It replaces human-driven feature engineering with automated feature learning. This flowchart tracks the basic process of analytical model building, beginning with the ingestion of raw data input. Before a machine can learn from this data, it needs a feature, a specific property derived mathematically from the raw input, to preserve its discriminatory information. In shallow machine learning pipelines, this extraction requires a handcrafted feature engineering phase. A human expert manually dictates how to extract specific variables. Those engineered features are then fed into an automated model-building algorithm to generate the final output. This pipeline contains a critical flaw. Manual feature design is incredibly labor-intensive, strictly bound by human domain expertise, and entirely rigid. Shallow machine learning automates the predictive model, but it traps the entire system behind a human cognitive bottleneck during the extraction of the features themselves. Deep neural networks bypass this limitation. They possess the architectural capacity to operate directly on raw, high-dimensional input data. Applying a deep neural network completely erases the human engineering bottleneck. The pipeline collapses into a deeply nested network architecture that performs feature learning alongside automated model building simultaneously. Inside this unified block, the network hierarchically assembles simple, low-level features into highly complex, abstract representations entirely on its own. This end-to-end abstraction enables cross-modal learning. The system can digest disparate data types, like streams of text, complex image matrices, and historical price data, and combine them into a single predictive model. By automating feature extraction, deep learning finally matches the native complexity of unstructured electronic market data. Because raw, unstructured data comes in vastly different formats, deep learning relies on specialized topological architectures to process it efficiently. Convolutional neural networks, or CNNs, serve as the primary architecture for computer vision and spatial data. This CNN grid architecture shows hierarchical stages optimized to extract spatial relationships. The initial layers identify basic edges, which subsequent layers aggregate into complex objects, like detecting specific products. Switching to a sequential layout, we see recurrent neural networks, or RNNs. This architecture is designed explicitly for sequential data structures. Notice the internal feedback loops. These loops form a memory state by routing information backward, a critical mechanism for forecasting time series data or translating natural language. Natural language processing tasks demand an entirely different mechanism called distributed representations. Rather than relying on simple word frequency, word embeddings project discrete language entities into dense numerical vectors. This preserves the exact semantic relationships between words within a unified mathematical space. By mapping the network's topology to the underlying dimensionality of the data, the system extracts the specific spatial or sequential patterns native to its input. Moving these models from laboratory performance into live electronic business environments expose them to harsh deployment realities. Deep learning generates its own features across millions of parameters. Because humans are removed from the extraction process, the network's reasoning is inherently untraceable, creating what is known as the black box problem. This lack of interpretability generates severe bottlenecks. Enterprise adoption, regulatory compliance, and system accountability stall when operators cannot explain how a machine arrived at a specific decision. Opaque reasoning also masks cognitive bias. Automated models blindly adopt and amplify human prejudices hidden deep within historical training datasets. Without transparent logic paths, developers struggle to detect these flawed decision heuristics until the model causes observable, real-world harm. Deep learning's greatest technical strength, its autonomous, untraceable feature abstraction, becomes its greatest operational liability when the market requires transparency. Live data environments also introduce concept drift. This occurs when the statistical relationship between the input data and the target variable changes over time. This graph illustrates a successfully trained analytical model. Its static decision boundary cleanly separates two distinct data clusters based on historical market distributions. Sudden competitor entries or gradual shifts in consumer sentiment alter the modern data landscape. As those real-world events happen, the data clusters migrate away from their original positions. The model's logic remains static. It now produces catastrophic predictive failures, incorrectly classifying the shifted distribution. Electronic markets are inherently dynamic. An intelligent system operating within them requires continuous tracking and retraining strategies to survive drift. Continuously training complex deep learning models from scratch to combat drift is resource-intensive and cost-prohibitive for most enterprises. This diagram illustrates transfer learning. Developers take a massive pre-trained general model and attach a highly targeted local dataset to specialize the model for a specific task. This practice drives the emergence of AI as a service marketplaces. Pre-trained analytical models are servitized and sold directly to enterprises that lack the vast computational resources to build their own. Importing foreign models introduces a severe security threat. Poisoning attacks occur when malicious actors insert hidden backdoors or classification triggers into public models before they are deployed by an enterprise. Enterprise adoption relies heavily on the emerging field of explainable AI to force transparency onto these complex, servitized architectures. As automated feature learning replaces manual engineering in high-dimensional environments, the technical focus shifts. To operate in modern electronic markets, we must secure, interpret, and safely manage the intelligence we've built.